And so welcome. This is our April seminar. My name is Dr. Andy Smallbone. I'm an associate professor at Durham. And as you've probably seen on social media, and I'm sure you're all keenly locked in to this, it's Earth Day today, and a day how we can all take action to improve our impact on the climate and the planet. And we're delighted today to host two speakers who are exploring some potential answers for decarbonising our economy. This event is organised through the EPSRC Network Plus for the decarbonisation of heating and cooling, and it's part of a series which are looking at different challenges on decarbonising the heating and cooling sector. So the next talk will be by Dr. Najjaran-Kheirabadi, who is a research associate at Durham. He's working on a new energy storage and new energy generation technologies, and is a visiting researcher in the heat and power divisions of the CEP Lab at Imperial. And he graduated with a PhD in 2020 in chemical engineering from Imperial College, where he worked on frost nucleation and human body convection. And Ahmad would be talking about advanced hybrid thermochemical compression, seasonal solar energy storage and heat pump system. Ahmed, please take it away.
Hello, everybody. Thank you for your introduction. I'm going to talk about advanced hybrid thermochemical compression, seasonal solar energy storage and heat pump systems, in acronym SOLAR S&HP. And I joined the group 1 year ago, and I started to work on the developing of experimental rig. Let's start with a brief introduction about the absorption technologies. The most common absorption technology we are currently using is absorption technology, which gas bucket is going to penetrate, diffuse into a liquid bucket and produce heat. And in some points, in some layouts, they are remove the pump in the system and use some inert gas like hydrogen, as you can see, which is called diffusion absorption process. And they are using hydrogen to remove the need for pumps. They are also widespread in the market industry, but our focus is on adsorption, which somehow the gas is going to adhere to a solid bed. Actually, this phenomena was investigated first before the absorption by Faraday in 1820s. When he tried to study the noble gas properties, he used a limber bended pipe, and he put silver chloride in powder in one side and put injected ammonia gas in the other pipe. And he realized that all the ammonia is absorbed by silver chloride. And then he tried to heat up the silver chloride and put the other side of the pipe inside a cold bath. And he realized that the ammonia liquid is going to form in the other side of the pipe. As you can see, the absorption process, you can see in here, the pressure versus temperature graph. And as you can see, once the starting process, if you look at here at the left side, you can see one of the dual bed absorption technology. Consider one of them. The first of all, everything, which is represented point A, every valve between the condenser and the evaporator is closed. And the absorption bed is slightly going to receive heat, and then some of the refrigerant, which is called the gas, the absorbed gas, is going to remove from the bed, but stay in the bed compartment because the valves are closed. And then the valve through the condenser is going to be opens, and then meanwhile the temperature inside the bed is going to rise, and somehow we supply heat to the absorption bed. So in an isobaric desorption, the whole gas is going to dissolve from the bed and goes to the condenser. And in the condenser, it starts, the valves would be closed and it start to reject heat surrounding. And this is the process we receive heat, or we also receive heat as well. And also then the evaporator valve is going to open. And once the evaporator opens, adsorbent bed is weak in terms of the gas. So it's going to absorb the evaporated gas in the evaporator and then suck every gas from the evaporator inside it. And this is the part which produces cooling. And the process is going to repeat. Well, adsorption is not a continuous process. So that's the reason people usually use, double compartment, double bed process to make the process continuous. The idea behind our project is to use the somehow surplus heat during summer and to store them as a chemisorption energy, and then use the energy for heat demand, also sometimes cooling demand as well, for the period of the year which there is no sufficient energy. As you can see in here, we have lots of energy, solar energy, but we are not going to use them. It's more than what we need for heating. So we are going to store them and dedicate them to the part of the year which don't have enough energy to consume. The thermal energy storage categorized into 4 different categories. Store the energy as a sensible heat storage, or maybe some molten salt or some other technologies, or latent heat storage like phase change materials, and absorption heat storage. With absorption, there is physisorption and there is chemisorption process. In physisorption, we usually, for example, we use water, and in chemisorption, we use ammonia as the working gas. And there is another method which is thermochemical heat storage without absorption, which we are going to store in CO3. We consider thermochemical storage, but we consider the absorption heat storage. So we consider ammonia in our technology. And there is lots of adsorbent used in such technologies. One of the indicators is the energy storage density. And as you can see, strontium chloride, expanded graphite, and ammonia is going to occupy less volume. So it represents a larger energy density for us. Also, the heat loss from sparing, strontium chloride and expanded graphite might be lower in compared with other, or even zero. Actually, for our project, we consider this one as well. There's other materials which is not presented in here, but it's manganese chloride, which we consider in our technology for case study as well. And the energy storage density is lower than strontium chloride, but there is other advantages for that material. As you can see, the adsorption process somehow showed in this graphic. We are going to heat once the bed is empty from the gas. It has appetite to absorb the gas to itself, and this adsorption process is going to reject heat to our surrounding. If we want to again use the gas, we need to heat up our adsorbent bed to release that gas to surrounding to produce cooling. This is the schematic of the ultimate device we are going to use. It's right now it's concept, but we are going to build a prototype based on it. We have several reactors, which all of them are filled with strontium chloride or manganese chloride, and water heating system is connected to all of them. So they are exchange heat with hot water, which comes from a solar module. And this solar module is sometimes it's not provide sufficient energy, not sufficient temperature, which we require for adsorption of ammonia to the strontium chloride. So the idea is to use a compressor to increase the pressure. Somehow once it has a compression ratio, which this side would be high pressure and this one would be low pressure. So the ammonia is going to dissolve in lower temperature once the pressure is low in here. So it's going to speed up our project to help our project, but the vice versa, we don't need it. So there is a bypass in here, which the compressor is not going to use, and then the vice versa is going to happen by itself. So as you can see in here, this is the compression work, which is going to somehow increase the pressure in this side, so that we can have condensation in here, and then we somehow dissolve ammonia from the reactor. Our project is defined into several 6 working packages. The first one is to understand what hybrid system we are looking for, and once everything is finished, we are going to check the thermodynamical optimization of the device, check the working pairs, check the adsorbent material is going to what's the adsorbability, what's the energy density, and so on. because we are using lots of equipment in our device, so we need to somehow size our evaporator, our condenser, our size of reactor, also the compressor selection, and we need to simulate the compressor. Check the compressor to see if it meets our needs in the system or not. So there's another thing, which is the controlling strategy, and using simulation and different equipments to check if our system can work. There's also some adoptions, as you can see with dotted lines. So if there is any problem happening in any working packages, we are going to somehow adopt them and then redo the exit process. And at the end, we are going to load our system to a bigger system to see if this storage system can integrate with other energy sources in a bigger scale. Also, we are going to consider the system, how much carbon dioxide is going to remove from our Earth. In here, you can see this is our system simulation. We just consider a reactor, a compressor, and a condenser. For an indication, we consider using an electric heater to increase the temperature of the water. As we said, okay, the solar energy is not always sufficient for our job, so we need to use a compressor to somehow cover that. Or there is another way, which is using heater to heat up the water comes out from the solar collector. We did it for indication, so just somehow to compare, but this is not our project. So in our project, we just consider the compressor. The basic of them is shown in here, and as you can see, the compressor is going to pressure in the condenser. So we would ammonia condensation in here. In the electric heater, we are going to heat up the ammonia. So then the ammonia can remove from the reactors and go to the condenser. This is two other different concepts, but using the compressor would be more efficient. As you can see in here in this graph, you can see that the storage efficiency of our system is at the best condition would be equal to 6. But for electric heater would be the same. But the point is, while we are using compressor, we are going to store more energy in kilowatt hour. For electric heater is something around 1. In the best condition would be something around 1500. But in here you can see it's equal to 4000. 4000. So definitely use compressor would have more benefit for us. However, the compressor needs electricity to be run. So we are going to somehow supply that electricity from the solar energy as well. And as you can see, once we are going to increase the compression ratio, which is going to increase our energy storage. However, we need more energy from the solar to convert into electricity to supply to the compressor. And for different compression ratio, you can see here, also, if we increase the compression ratio, we may need extra volumes. So we store more energy, more heating energy, but we need more volume as well. Well, in here, these results come from the simulation. It's not from the experimental results. So that's the reason you can see everything is perfect in these graphs. We are not right now in the experimental stage, so these results come from the simulation. You can see the level of carbon emission for every technologies, heat pump, gas boiler, and our system with electricity grid. If the number of module is going to involve in the reactor, it's written outcome, but it's a number of module which is involved in the heating, and its compression ratio with grid electricity, which is connected to the grid electricity. Using electricity from the grid, and once we are using the solar energy to supply electricity to our compressor for the compression ratio of 4. And as you can see here, the gas boiler always shows better results. For our two experiments, you can see once we use the solar energy to supply our compressor, the carbon emission would be definitely lower, better than any other technologies. However, as we said, we may need to supply more solar panels to meet the compression electricity need. And if we consume it from grid, you can see it's in the second place of better technologies to produce lower carbon emission. Achievement so far in experimental section, you can see here we built an early prototype. which contains two reactors. One of the reactors are filled with strontium chloride and expanded graphite, and the other is manganese chloride with expanded graphite. And we are going to run the reactors each time, just somehow to compare adsorbent bed together to see which one is better. Well, said in the literature, it's presented that the strontium chloride would be better. Also, we consider an oil-less compressor to mount it on our system to speed up the process. And right now, it's not connected to a solar heater because, so we need to find a place for it. It's a big rig, so the outer experiment wouldn't be somehow feasible. So we are going to simulate that solar energy with an electric heater in here. The next stage is to preparing the material. As you can see, this is the absorption bar. We are going to use, it's a thin bar, which is surrounded by a mesh tube. And in between, there is an expanded graphite and the salt mixture. And they are compressed a certain density. If we increase the density of the salt inside the fin, we are going to increase the heat transfer ratio. The point is, we are going to reduce the absorbability of the mixture because it's going to reduce the porosity. So ammonia is hardly penetrating inside the expanded graphite. And this is our press machine, which is filling the material inside the fin tube. It's not a straightforward process. We have to put the fin tube and the mesh inside this pressing machine, and then use some specific sticks with power of 5 tons to press everything to the system. And we need to discretize our filling process because we cannot press everything together. So we need to use the whole length of the fin. So we discretize into certain levels, 5, 6 levels. And then in each section, we are going to fill the system with 10 grams of salt mixture until we have some strontium chloride. It's 250 grams of salt needs to be filled in each tube. Also, we need to consider the dynamic of the system to see how fast our system is going to heat up and how fast it's going to cool down. So there is another side experiment is designed to check that one as well. And right now we are changing our fin tubes. In this very picture, as you can see, it's the fins are connected through glue to the core pipe, but in the new layout we are going to use is welded fins for our purpose. And just to give you a rough estimation about how fast the transfer would be different between welded and glued tube, rising the temperature from 45 to 80 degrees Celsius in the glued tube takes something around 5 minutes, and in the welded tube it takes less than a minute. So says that okay, the welded tube might be better. I want to thank you from my principal investigator, Dr. Jive Mai, and also my co-investigators, Professor Tony Roskilly, Dr. Huashen Bao, and my colleague, Dr. Salem Ebadi, who recently joined our group. Also, my colleagues in University of Chester, Professor John Consul and Yusuf Khalid. Also, our project partners, Gromville, Power, Arup, Glen Dimplex, and Lewis District Council. Also, EPSRC for funding our project. Thank you so much, and I'm happy to answer your question.
Thank you, Ahmed.